Hi everyone, it's Kira Garfola with Greenville Tech's Math 109. Today we're going to cover section 3.3, which is piecewise and power functions. So we're going to take a little bit of a turn from earlier parts of chapter 3 where we were only dealing with quadratics, and now we're going to talk about what I think are some kind of cool and fun functions. So we're going to start by talking about piecewise functions. So first of all, what are piecewise functions? So a piecewise function, or a piecewise defined function, is a function that is broken into several domain chunks, where each chunk has its own formula. You can think about it as piecewise, it's all pieced together. You have different pieces of graphs and you're going to put them together. Here's an example of one that we have. You can see that this is quadratic, right? It's the start of a parabola, but then it stops that and it jumps to another one, and then it stops that and it jumps to another one. We're going to use a piecewise function to find the value of f of x at a certain x. You need to follow a couple of steps. The first thing you need to do is look at the domain rules and pick your chunk that you need to be using. Then all you have to do is disregard everything else, only pay attention to the chunk that matters, and find the value of f of x for that value of x. Let's look at an example. So let's consider this piecewise function, where 0 is less than or equal to x is less than 2. We have f of x is negative 2x plus 4. Where x is greater than or equal to 2, we have x squared over 2. So first we want to find f of 1. Well, where does 1 belong? 1 isn't greater than 2, but 1 is between 0 and 2. So f of 1 is going to be here, and so we're just going to plug 1 into this top equation. So f of 1 is going to be negative 2 times 1 plus 4, which is going to give us 2. That's it. That's how we find f of 1. Now let's find f of 2. We have to be careful here because 2 is in both of these chunks, but remember that this strictly less than 2 doesn't include 2. It's all the way up to 2, so 1.99999, but not 2. And this next one is 2 is less than or equal to x, so 2 is included thanks to this equal to. So it's this chunk that we'll be working with. We plug 2 into this, so 2 squared over 2, and we get the value of 2. So f of 2 is simply 2. If we want to find f of 3, we can look and see that 3 is greater than 2, so it's going to go into this second chunk also, and it's going to give us 3 squared over 2, which is going to be 4.5. Lastly, we want to find f of negative 1. So if we look at these chunks, negative 1 is certainly not between 0 and 2, but negative 1 is also not bigger than 2. So since this function isn't defined at x equals negative 1, then there's no solution. We just say that the function value is not, it doesn't exist. It's not defined. Now, a lot of people either love this or hate it. I tend to like it for the most part. And graphing piecewise functions is something unique. We saw a graph of it earlier when we were talking about introducing piecewise functions. So basically, you're going to graph each chunk on its own. Some people like to kind of draw different portions of the graph, draw little dotted lines to separate it. But you're going to just graph it like you would across the whole graph, but you really only want to include that certain part of the domain that matters. Generally speaking, I like to start with my endpoints of each chunk of domain. It's a good place to start. Now, even if you have a strictly less than or a strictly greater than, you can still plug that value of x into the equation. Just remember it's going to have an open point, not a closed point, to represent that strictly less than or strictly greater than. So let's graph our earlier piecewise function. First, we're going to look at that first chunk. So we want to graph negative 2x plus 4 between x equals 0 and x equals 2. So 0 is included, so it's going to be a closed point, but 2 is going to be an open point because of that strictly less than. So if we look at the endpoints, we have x equals 0 first, so we plug 0 into here to get the value of 4. So we get the endpoint 0, 4. That one is a closed point because it's less than or equal to. And if we do the same with 2, we're going to get 2, 0 as a point. But remember, it's going to be an open point because of the strictly less than. This is a linear function, so we really only need those 2 points, and we can plot them between 0 and 2. Now, if we want to graph the second chunk, we're going to have our endpoint at x is equal to 2. And it's going to be a closed circle because the equals is included here. Plugging x equals 2 into here, we get 2. So our endpoint here is going to be 2, 2 as a closed point. Now we can see that this is going to be a parabola because it's a quadratic. You can plug extra points in as you need to get the full shape of the graph. And this is what we see. Right here is our first chunk. So from x equals 0 to x equals 2, it follows that negative 2x plus 4. And then starting at 2, remember this open hole right here. So starting at x equals 2, it comes up to here and it follows that x squared over 2 rule. So it follows this parabola shape. Now take a few minutes to give it some practice. I want you to graph the piecewise function given below. I've given you some starting points. So use x equals negative 2, x equals 0, and x equals 3. And then you're going to graph the function. Go ahead and hit pause, work it out, and hit play when you're ready. Okay, so the solution here, we know that if x is less than 0, y is negative x, and if x is at least 0, y is x. So even though there's a strictly less than here, since if you look at your endpoints, f of 0, it's going to be the same value no matter whether we use negative 0 or 0. It's just 0. So this one would be open, but this one's the same value as it's closed, so the closed prevails. So x is less than 0, we're going to have negative x is y, and x is greater than 0 or equal to 0. We're going to have x is simply equal, or y is simply equal to x. So this is the graph that we get. There's 2 linear functions. This one is negative 1 slope. This one's positive 1 slope. And they meet in the middle at the origin. Again, make sure you can work through these because you will see questions like this again. Now that graph right there that was the V brings us to our next point, absolute value equations. So to solve an absolute value equation, such as f of x in absolute value bars equals a, you're going to follow a handful of rules to help simplify it for you. First of all, value of a is greater than 0. You're going to solve f of x equals a and f of x equals negative a, and any of the solutions that meet those criteria will give you a correct answer. So all solutions are valid. If a equals 0, you're just going to solve for f of x equals 0. That's going to give you your solutions. Now, if a is negative, there is no solution because remember the absolute value is always going to be a positive or 0 number. It's a non-negative number. So if you have nothing on this side except an absolute value bar function equals a negative number, then no solutions exist. Let's look at a couple of examples. First, we want to solve absolute value of x minus 2 equals 6. So here we notice that 6 is positive. So we need to solve twice. We need to solve x minus 2 equals positive 6 and x minus 2 equals negative 6. So solving x minus 2 equals positive 6, we're going to get 8. And solving x minus 2 equals negative 6, we're going to get x equals negative 4. So our solutions are x equals 8 and x equals negative 4. Now, you give it a try. You want to solve the absolute value of x squared minus 5x equals 6. Again, feel free to pause the video, work it out, and then come back to check your answer. Now, in this one, just like before, we see that our value of a is positive because 6 is above 0. So we need to find x squared minus 5x equals positive 6 and x squared minus 5x equals negative 6. This is going to put together a little bit of our information from 3-2 where we had to solve quadratic equations. And the first one we're going to get is going to be x squared minus 5x equals positive 6. Remember, we need to move everything to one side, and we can actually factor that into x minus 6 and x plus 1. So our solutions to that piece would be x equals 6 and x equals negative 1. Now, we also have to solve for x squared minus 5x equals negative 6. We pull that 6 over again, so we just have a 0 on the other side, and we get solutions of x equals 3 and x equals 2. Now, we've solved a quadratic twice, so we're going to get 2 answers per, so a total of 4 answers are valid. Our values of x are going to be negative 1, 2, 3, and 6. Now, I used factoring above because that was the simplest and most straightforward to me at the time. You could have used a graphical method. You could have used factoring. You could use quadratic formula. You could use any of those methods that we talked about before. This brings us to other famous functions called power functions. And power functions are written in the form y equals a times x to the b, where b is not equal to 0. So a times x to some power. There are some special cases that you want to be familiar with. The picture to your right shows a lot of those special cases. They're in your textbook with longer explanations and much prettier pictures, so definitely take a look there. But most of these are going to come back for us to see. So you'll want to get comfortable with them. You'll see them a lot in your homework, but you'll also see them, especially as we move forward with this unit and later in our course. I call them parent functions because they seem to be famous functions that we're going to see and transform in later sections. One of the most common uses of power functions is to talk about direct variation. So we have something called direct variation as the nth power of x when y equals k times x to the n for some number k. K is called our constant of variation, and oftentimes we have to solve for it first. So let's learn this one from example. Suppose the weight of a ball varies directly as the cube of its radius. So we know that a ball weighing 380 grams has a radius of 2 centimeters, and we want to know the weight of a ball with a radius of 5 centimeters. So the first thing we're going to need to do is set it up and solve for k. So we know just from the information that y equals k times x cubed, since we're varying directly as the cube. It tells us that in the original problem. We also know that y is 380 when x is 2. So we can plug that in and get 380 equals k times 2 to the third because we know that information given. Now we're ready to solve for k. So looking at 380 equals k times 2 to the third. 2 to the third is going to give us 8, so 380 equals 8 times k. If we solve that, we see that k equals 47.5. So now we can go back and we know the actual relationship. We know that y equals 47.5 x cubed, where y is the weight and x is the radius. So we can finally answer the problem that was posed, which was how much does the ball weigh if the radius is 5? At this point, all we're doing is plugging 5 in for x. We're solving f of x or f of 5 here. So plugging that in, we see that it's 5937.5 grams. Make sure you can practice this. Make sure that you can replicate this because it does come up on homework and beyond. On the other hand, with direct variation, as one goes up, the other goes up. But on this side, we have something called inverse variation, and that happens when we have y equals k over x for some number. So instead of having y equals k times x to the n, we now have x on the denominator. Terminology-wise, we usually say that y varies inversely as x, or y is inversely proportional to x. And we can actually combine this with what we talked about last slide and say that y is inversely proportional to the nth power of y. So it's that inverse that puts it down there in the denominator. So if it's inversely proportional to the nth power, then we have k over x to the nth power. Basically, you're going to do everything the same as you did before. You're usually going to have to use a known data point to solve for k. Then you have your statement of proportionality, and then you can plug other values of x in to make other predictions. Let's look at an example. The illumination from a light varies inversely with the square of its distance from its source. If the illumination 30 feet away is 60 candela, what is the illumination at a distance of 20 feet? So first we need to solve for k. We know that at 60, first of all, we know it's varying inversely with a square. So we know that it's y equals k over x squared. So here we know that 60 equals k over 30 squared because it's 60 when the distance is 30. If we solve that for k, we see that k is 54,000. So that means that we know that y equals 54,000 divided by x squared. Now we can plug any value of x into that to solve. The problem asks us for the light at 20 feet, so we need to find f of 20. So f of 20 equals 54,000 divided by 20 squared, which is going to give us an answer of 135 candela. So at 30 feet away, it's only 60, but at 20 feet away, it's all the way up to 135. So wrapping up this section was a particularly mixed bag of things, right? We talked about a bunch of different things. We talked about piecewise functions, power functions, and then direct and inverse variation. They're all kind of related, but they're also all kind of different. Remember to practice, practice, practice. Again, this is a very heavy chapter. It's a very heavy unit. So make sure you're doing your homework and any other assignments that you have. If you need help, make sure that you get it. There are other videos and lots of extra lecture notes within the Blackboard page where you found our lectures. There are textbook resources available for you, including other videos and other practice and things like that. You have my office hours and my email at any time. And you also have the Math Center, which you can have free tutoring kind of on demand. They do it in person. You can stop by. They say that appointments are first, but usually drop-in is fine. And you can also attend the review sessions. They also have virtual one-on-one sessions that you can reserve. So definitely check out the Math Center. In our Blackboard course, there's a lot of information on the banner and on the announcements about the Math Center. Thanks for tuning in. I know this was heavy. I know these last few sections have been heavy, but practice, 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 and you will do great. Have a great day, and I'll see you next time.